Hello, everyone. We're going to look at our lesson 7 from Unit 3 today. We're going to talk about um, the reasoning behind similarity statements. And one of the better ways, right, to kind of understand similarity is through dilation. And we've seen that um, so far in this unit a bunch. We've seen kind of like a center of dilation, let's say in this case A, and we sort of push out a figure, right? You can see how it makes a triangle here, right? We kind of expand out this line. And so long as we stay with the same slope of this line, right? As long as we kind of stay consistent with our dilation, right? What we're going to end up with are similar figures. Now, this type of imagery can cause a little um, tough. It can be a little tough for people to see, and it can cause some issues because this is a special type of kind of similar triangle set. But here's what I kind of want to show you what I mean here. So if we take, let's see, this triangle here, and so I'm going to kind of do a crude drawing of it. Right, we can see that the lengths are 3, 4, and 5. Okay, right? So a similar triangle to it is going to have, again, all the same angles, but it's going to have all of the sides in the same ratio to this 3, 4, 5 triangle. Okay, now, when you look down here, right, we see some of these other numbers. We see 9, 15, and 16, right? And those do relate to the numbers 3, 4, and 5, but not in the way that you might think, right? This is 3 times 3, this is 4 times 4, this is 5 times 3, right? There's not a common relationship there. But that's because we're not looking at a similar figure, right? This shape here is a trapezoid where really the entire shape, if we were to kind of ignore this line, that's the big triangle, right? So we're going to draw this out, right? So imagine the big triangle, okay? So the bottom is 16, right? Right, we can see that the bottom is clearly 16, but the sides are not 15 and 9. The sides, we need to combine the lengths of the other shape with kind of that trapezoid shape to make the bigger triangle, right? So 3 and 9 make 12, 5 and 15 make 20. And this is a way for us to see again um, the similarity between the two figures, right? We know that if those two lines are parallel, again, we're going to have the same angles. But if we see a constant relationship between the sides in these two separate triangles, we're going to have that similarity, right? So if we look 5 to 20, right, we would get that by multiplying by 4. We would get 4 to 16 by also multiplying by 4. And we would get 3 to 12. Guess what? Multiplying by 4. So if we did all of these ratios, 5 over or 20 over 5, if we did 12 over 3, if we did 16 over 4, we get all of the same ratios. They all point to 4 over 1, again, which is 4, right? So remember, we're always doing, again, the end over the start, okay? End over the start. But we need that constant ratio or else it kind of falls through. Now we also need the constant, we need all of the angles to be the same as well. But again, if we don't know information about the angles, with triangles particularly, we can just look at sides. And if the sides have the same ratios, then it's going to work. It's special about triangles. So if we look here at our figure, it says, are these shapes similar, right? So we need the same angles and we need the same ratio of sides. Well, if you look here immediately, I have an angle, and this is maybe kind of hard to see, but there are 4 arcs. So this is 4 arcs, right? There's no figure over here that are four arcs, right? So even though I don't know these other angles down here, and those angles could match the other triangle, this is going to be a no pretty much right off the bat because, again, we're missing that angle. But we could also look, again, at just the sort of the small, medium, and large legs of each of these triangles and see how they compare, right? If we looked at the smallest side of the triangle on the right, we have 34. Okay, we see this. On the left side, the smallest side is also 34, right? So notice that these are the same numbers, right? We're going to expect these would have to be 1-to-1, right? Every side would have to match in order for this to work. We can pretty easily see in just a second that's not going to work. If we look at our middle side, we see 50 and 50. Right, this is 1-to-1, right? So that's close. But if we look at our last side, we have 52 for our right side and 55 for our left, right? Notice how that's not 1-to-1, right? So there's one side that's just a little bit off, which is going to kick the angles off and so on, right? So even though we can tell pretty early that these are not going to be similar, this is kind of the logic of how do I know exactly that that's true? How can I prove it? And that would be because I can find two sides that are corresponding that do not um, have the same ratio as the other ones. Okay, so same type of problem. Are these similar shapes or not? Right. So again, let's test this out. Let's see what we're looking for. We're looking for all of the same angles, and we're looking for the ratio of the sides. If I look at the angles on the left, I see single arcs and a double. I see single arcs and a double. So the angles are definitely matching up with what I want. And if you remember, guys, again with a triangle, AAA does tell us the triangles have to be similar, right? So we're going to see the same ratio of all the sides here. Let me, and we'll show you. So again, small. Now these two sides here, um, we're just going to have a small and large, okay? Because again, we can see the lengths here. We've got 50s and 30s. They each have a pair of equal sides, and then they have a side that's smaller, right? We have the 12 and the 20, right? Those are smaller than the other ones. So let's compare, right? So let's compare. So on the left, we have a 12. On the right, we have a 20. So 12 compared to 20, right? So we could divide this a few times. But again, each of these is divisible by 4. So this is the same thing as 3 by 5, right? That's the same idea, right? 3 times 4 makes 12. 5 times 4 makes 20. So this would be what it boils down to. 3 units over here, 5 units over here. And we can see that the longer sides here are going to be 30 to 50. Again, this is 3 to 5, right? We can divide each side by 10. So this is yes. Now we could have told this earlier as well, but we see the proof down the line. And we can look at again, the ratio has to be the same across the figures.